Well, I actually look at my career in kind of an interesting way because I've kind of done a full circle. I started out in the early 70s as a civil engineer with environmental leanings because that was in the days where there was acid rain. We were looking at cases of salinity intrusion in the San Francisco Bay. There was really the first beginnings of the environmental movement. I fell in with a bad crowd. I fell in with a bunch of high-energy physicists because I was interested in building fairly high-end instrumentation at the time. And that led me into the computing industry because sooner or later I decided that, well, if I was going to do computing, I was going to do computing as a professional and not as just an amateur. That eventually led to building a machine. That led to coming to Microsoft, working in the Windows division, and then sort of taking a time off, kind of to step back, look back. I found what Jim Gray was doing with Alex Saleh to be really, really compelling to me. Science is changing right now, and it's changing as an artifact of computing technology. The internet, cheap sensors, and commodity computing. And it's really driving a data deluge, flood, tsunami, depending on what field you're in, call it something different. People are drowning in data, and it's two kinds of drowning. It's drowning in complexity, not knowing how to handle it, as well as resources, not having the computing necessary to actually do the data processing. So kind of coming full circle, when I got back to Jim Gray's lab, I found an old colleague of mine that I had been in grad school with, James Hunt at University of California, Berkeley. He had recently gotten involved in something called the Berkeley Water Center, an interdisciplinary group at Berkeley, trying to grapple with some of the more interesting water problems in the state of California, as well as Dennis Baldacci, my collaborator also at UC Berkeley, who's led me into working with carbon climate scientists. So it's a big kind of circle. I don't quite know how I got here, but it all seemed very logical at the time. Last summer, working with one of Dennis Baldacci's students, we prototyped a service for doing satellite imagery processing that I'm really excited about. One of the things that I kept running into as I was talking with various scientists, and particularly their postdocs, because the postdocs have to do the grunge, is that dealing with satellite imagery is something that's still the faithful, the priesthood. You have to know about this reprojection and that reprojection. You got to know about this NASA website, and then you got to deal with this, that, and the other thing. Well, one of Dennis's students, Young-Ril Ryu, wanted to compute the water balance across the United States because he had done it for Korea. Now, Korea is a pixel, and the United States is about 1 million pixels. Scaling up the calculation over 1 million times really is something where Azure's pay-as-you-go model is wonderful. Why? Because we were really going from a calculation that was doable on a desktop to a calculation that where the reprojection for each year is about 2,500 hours, 2,500 hours of computing time, something that would be long enough that Young-Ril's small daughter would be growing up. In addition, just uploading the imagery for a year takes several days. So drawing that same imagery over a university network, particularly that last little long haul step, which is not always good at most universities, would be particularly problematic. So we're able to move from NASA websites into the cloud, do the reprojection in the cloud, scaling with 150 instances this summer, but then we actually run a custom reduction step. So after doing all of the source imagery reprojection, we're actually doing the computation that Young-Ril's interested in. We take 400 to 500 gigabytes in, reproject 400 gigabytes, and then reduce down to 5 gigabytes. The 5 gigabytes then we download. That's something that is easily downloadable to a university. So what are we leveraging here? First, we're leveraging the fast networking. Secondly, we're leveraging the high amount of compute, because after all, we want to do 10 years of this. And thirdly, we're actually being able to run the reduction step again and again and again as we iterate around to get the right algorithm for science. What excites me about this in a number of ways is the reprojection step is really reusable. Young Reel has a colleague at his old university that has contacted us and wants to actually do the calculation for South Korea. We have other colleagues in Europe who want to try a similar calculation. They won't have to deal with that level of grunge. They can get on doing the science. One of the things that really has changed in science since when I started is the following. First, we grew up with the notion that in hydrology that the past was a good predictor of the future. That's just no longer true with climate change. One of the things that means is we have to come to grips with how do we predict the future. For hydrology, one of the notions that Jim Hunt has put forward is the notion of using related watersheds, right? For predicting San Francisco, perhaps somewhere more southerly in California would be a good thing. Other scientists are trying some correlating similar sorts of questions. So we're struggling now with the question of how do we predict? All of that means computing. The other thing that definitely is kind of a vision thing is what this data deluge is doing to science. It is changing the way science gets done. I belong to the first generation of non-high-energy physicists who were taking data natively digitally. I took my thesis data digitally. I walked out with tapes and I was done. The students before me, by and large, had either used analog intermediaries or a pencil and paper. Okay? Dealing with that level of data and making it commonplace and making it understandable to postdocs, so they're absolutely able to get on with the science and not do the grunge, right? Remains a challenge, I think, for us as an industry as we encapsulate key algorithms and embody services that can lower the barrier to entry by reducing the complexity. And as a society, right, we need to figure out how we do science together. Doing synthesis science means that we're spanning not only the computer science to science discipline, but also across science disciplines. When I first engaged with carbon climate scientists, I thought they were all the same. No. There's biologists, and there's micrometeorologists, and there's ecologists, and there's soil people. So they all speak slightly different languages. Ontology remains a very fundamental question going forward, and one where IT in particular can help. When we talk about global warming, I want to talk specifically about the climate science that I'm working with, which is not necessarily what we might do as individuals by cutting our carbon footprint. It's not what we do as a society in terms of changing technology, but specifically and helping to enable the scientists who are struggling, trying to figure out what does global warming mean? How do we predict a future where we cannot use the past? It's really, really great watching the folks come together there, because there's a recognition in that community that the problem is bigger than any individual. And you see groups like the North American Carbon Program coming together, trying to grapple with what is the best modeling approach, what is good data to compare models, how do we actually acquire data and synthesize data. Unlike physics data, which spews out of the LHC, environmental data is, first of all, a gathering problem. You have to gather data from here, here, here. Climate data, particularly modeling data, you can get modeling data, but you immediately pair that with field data. You get remote sensing data, you want to pair that with, again, field data. That gets to one of the other things that I get really excited about, which is citizen science. When we start talking about field data, there's only so many scientists in the world. If we really want to come to grips with what's going on in the field, we have to engage the citizens and amateurs. How do we go about doing that? How do we break down the barrier so that citizens can go out, make an observation, like with the National Phenology Network, like with my collaborators at UCLA who've done www.what'sinvasive.com with the Forest Service, so that they're able to bring data that a scientist will trust enough to use. It gives us a much wider coverage. It's the so-called long-tail data. It's not big, it's not petabytes, but bringing it all together, being able to have a living, breathing data set being so critical to understanding the puzzle between the models, the remote sensing, and the globe.